So in my previous lecture, we were talking about data link layer protocols, in which we explored the utopian simplex protocol, and then we started talking about stop and wait automatic repeat request ARQ protocol. So that stop and wait protocol was a little more restrictive as compared to the utopian simplex one. So here receiver is having a finite processing speed, frames are supposed to be get corrupted or maybe even lost completely, could be dropped also, and receiver is going to send an acknowledgement for every valid frame that it is going to receive. So ARQ, if we look into the complete idea of ARQ, yes, it is kind of simple, in which your automatic repeat request, if we talk about, that means it sends the data packets and request acknowledgement of receipt from the receiver end. If the sender is not receiving an acknowledgement from the receiver, even if the packet is being delivered, the acknowledgement is missing, it assumes that the packet was lost and corrupted and resends it. So basically, in a nutshell, we can say the protocol works by transmitting a single data packet, waiting for an acknowledgement before sending the next packet. So again a single data packet is being sent, wait for an acknowledgement, if acknowledgement is not being received, repeat the transmission or repeat that particular frame. So in this ARQ protocol, we can say sender sends the data packet, waits for the acknowledgement from the receiver side, receiver sends an acknowledgement back to the sender indicating that the packet has been successfully received. If sender is not going to receive an acknowledgement within the specified transmit within the specified time frame, it retransmits the entire packet, and that is why, because of this whole stop wait functionality, this protocol is known as stop and wait, because sender is waiting for the acknowledgement before sending the next packet. And because of this hide and seek of stop and wait frame and acknowledgement, the protocol becomes actually slow, as it does not allow for pipelining or sending multiple packets at once. So this is one of the we can say a drawback of your stop and wait ARQ protocol, which is going to be kind of resolved in our upcoming more complex protocols. So this protocol is commonly used in such situations where data loss is not frequent, or where the cost of retransmitting a lost packet is actually low. And this is the figure which we have kind of seen in our previous lecture also. So if you can see that kind of a thick cross in which a frame 0 is not able to kind of get delivered at the side B, after waiting some time A is resending it. In for the next cross, if we talk about, acknowledgement is not being kind of delivered at the sender's side. So sender is again going to receive that particular frame 1 for which acknowledgement is not being received. And now frame 1 is actually in duplicates at the level at the machine B. So it is the responsibility of the receiver to discard the duplicate frames. What all are the components, if we talk about this particular stop and wait ARQ protocol? So communication is still simplex. We have not assumed any scenario in which the data is also traveling from A to B as well as from B to A. We haven't talked about that scenario. So still we are talking about simplex communication in which data is traveling only in one direction, that is from sender to receiver. Stop and wait functionality is there. Sender transmits the single data frame, stops and wait for the confirmation from the acknowledgement before sending the next frame. Now timeouts are kind of essential components. A timer is started by the sender when a frame is sent, and within the specific time period your sender is expecting an acknowledgement. If an acknowledgement is not received before the timer expires, the sender assumes that the frame or the acknowledgement was lost and then retransmits the frame. Now in order to keep the track of which all frames are being received, which all frames are being kind of for which the acknowledgement has been sent, each frame is assigned a sequential number. But this stop and wait protocol being such that one particular frame is being sent and then the sender is waiting, only the numbering between 0 and 1 suffices. So, this allows the receiver to identify and discard duplicate frames that might arrive due to retransmission, and this scenario of duplicate frames being arrived at the receiver's end we have seen in a figure. So, only 0 and 1, that kind of numbering is being is, we can say, sufficient, because it is kind of one to one frame transmission between sender and receiver. So, at the receiver's end it is receiving one frame, sending the acknowledgement, and then your sender is receiving the next frames. Acknowledgement obviously is an important component. Acknowledgement, you can say it is a kind of dummy frame which is being sent to the sender in order to confirm the successful reception of a data frame. Error detection, if we talk about, we have initially started with that the channel is itself noisy. So, when we say it is a noisy channel, error detection mechanisms are required, because of this noise errors may get kind of introduced inside the inside your data. So, error detection mechanisms like checksums are included in the frame to help the receiver identify if the received data is intact or it is corrupted. If the frame is corrupted, the receiver simply discards it, and it is not going to send kind of acknowledgement of this. Now, with this stop and wait protocol, if we summarize the sender section, it gets a packet from the network layer, add a sequence number, it could be 0, to the packet to create a frame, sends the frame to the physical layer, starts a timer, waits for an event of either acknowledgement coming up or timer getting expired. These two events can be there. At the receiver side, what all actions are being taken or performed, receiver receives the frame from its physical layer. Obviously, it checks for the errors, for example, using a checksum, because I have told you the channel is noisy. If the frame is valid and its sequence number matches the expected sequence number, then the receiver extracts the data and delivers it to the network layer, and then sends an acknowledgement back to the sender, including the sequence number of the acknowledgement frame. Now, here the point which says that if the frame is valid and its sequence number matches the expected sequence number, then it extracts the data, delivers it to the layer above, and then after all this functionality, it sends an acknowledgement back to the sender is very important, because sending an acknowledgement back to the sender before checking that frame is valid or not is not going to help, because after getting the acknowledgement, your sender is not going to retransmit it, and here at the other end you are going to discover that frame is not valid. So, that checking about the validity of the frame in case of kind of the data which is valid or not, or this is the frame which is being expected, is important to be done before sending an acknowledgement back to the sender. Now, after getting the acknowledgement, if sender receives a valid acknowledgement for its frame within the timeout period or before the expiry of the timer, it stops the timer, prepares the next frame by incrementing the sequence. Initially it was 0, then this time it could be 1 or something of that sort. What will happen if the sender's response or sender's timer is going to expire? What will be the sender's response to timeout? So, if the timer expires without getting a valid acknowledgement, sender is going to assume that the frame, or it could be an acknowledgement of that particular frame, is lost. So, the sender retransmits the same frame with the same sequence number. So, the same frame for which acknowledgement is not being received is being kind of, we can say, retransmitted. Then it could be an acknowledgement which is the missing one. Frame is already kind of at the receiver's end, frame is already received at the machine B or the receiver's end. So, in that situation your sender is going to transmit it again, already it was being received. So, that means duplicate frames are there. So, if this situation happens, the receiver will see that the sequence number is not matching the one with the one it is expecting. So, for example, it has sent an acknowledgement for 0 which is not being received at the sender's end, and kind of again it is going to get the frame 0 while the frame 1 was expected. The receiver will see that the sequence number is not matching the one it is expecting. So, it is going to discard the duplicate frame and resend the acknowledgement for the previously received frame. Now, this is very important. If your receiver is not going to resend that acknowledgement, how your sender is going to identify that yes, okay, this particular frame is being kind of received. So, in order to inform the sender, it is important from the receiver in case of getting the duplicate frames, it is important to resend the acknowledgement for the previously received frame, so that sender is going to be informed that this is being received, and now it is kind of we can say it is ready to receive the next frame. Now, we have understood the whole working, all the components as well as the functionality of your all other scenarios that kind of duplicate frame handling and so on and so forth. In case of simplex stop and wait ARQ protocol. Now, what was the problem? The problem was that we can say that it is very slow, looking into or degrading the efficiency of the whole network, because it is kind of stopping after sending one frame, waiting for the acknowledgement, and duplication is also there. So, all these problems are there as far as your stop and wait ARQ protocol is concerned. Moving further, let us consider a new protocol which is kind of a sliding window protocol. I will not say this is one protocol, this is having some different versions. We can call that it may be it is having a few protocols, or it is having its own versions of few protocols. So, sliding window protocol actually again a data link layer protocol which allows sending multiple packets. Now, here is one kind of disadvantage of your stop and wait protocol which is being taken care of here. Here multiple packets can be received before receiving the acknowledgement, and for this whole thing a window is being kind of managed. So, we using a window to manage the packet flow, this functionality can be kind of achieved. How, that we will see in our upcoming discussions. So, obviously it is going to improve the network efficiency and network throughput, especially if I am talking about a long distance or a high latency connections. So, one thing which is kind of sure here is here is a window to manage this whole packet flow. Multiple packets can be sent even before receiving the acknowledgement of the previous ones, and how this is going to be kind of taken care of, or how this whole functionality is going to be managed, that we will look into. But before going into the details of our sliding window protocols, we need to look for we need to look in some of the terminologies which are important. So, in the sequence of terminologies, the first one is transmission delay. Transmission delay is being kind of denoted by a capital T and a small t, which is in the subscript. So, transmission delay, as you can see, it is the time to transmit the packet from the host to the outgoing link. Now, if B is the bandwidth of the link and D is the data size to be transmitted, then the transmission delay will be D upon B, which is data size upon the bandwidth of the link or of the channel, we can say. So, time to transmit the packet from host to the outgoing link is the transmission delay. Another important term which is going to be used soon is propagation delay, denoted by T, and within the subscript it is P. So, the transmission delay was denoted by T. So, when are we talking about delays, we are denoting them by capital T's. If this is transmission delay, then it is going to be a subscript T. If it is propagation delay, it is going to be subscript P. So, propagation delay, if we talk about time taken by the first bit transferred by the host onto the outgoing link to reach the destination. Now, obviously, when I am talking about the first bit transferred by the host onto the outgoing link to reach the destination, it depends on the distance d and also the propagation speed s. Now, this propagation speed s actually depends on the characteristics of medium, whether it is a coaxial one or kind of a twisted pair, or it could be a fiber optic network when I am talking about the physical medium, or it could be any other. So, this propagation delay, which is denoted by T of P, is actually the distance which is to be covered, denoted by small d, divided by propagation speed s, which depends on the characteristics of medium. So, propagation delay is the time taken by the first bit transferred by the host onto the outgoing link to reach the destination. That is what propagation delay is. Moving further, we have next term, which is kind of efficiency. So, efficiency, we can say it is the ratio of total useful time to the total cycle time of a packet. In case of stop and wait protocol, if we talk about the total time, which is denoted by double T. So, double T here is the propagation delay plus the transmission delay. So, T of P plus T of T, the two terms which we have already seen. Then T of T for acknowledgement and T of P for acknowledgement. So, in stop and wait protocol, please recall there is a data which is going from sender to receiver, and then there is a acknowledgement which is coming from receiver to sender, and both are having their own propagation delays as well as transmission delays. So, transmission delay for data, propagation delay for data plus transmission delay for acknowledgement plus transmission delay for propagation delay for acknowledgement. So, T of T data plus TP data plus TP acknowledgement, which is twice of, so we can say this is T of T plus 2 into T of P, that is what the total time going to be. Now, acknowledgements we can say are very less in size, so their transmission delays can be neglected, and because of these delay in or neglecting the delay in transmission for your acknowledgements, our whole this equation is coming to T of T plus 2 into T of P. Now, efficiency, when I am talking about, it is defined, as I have told you, as ratio of total useful time to the total cycle time of a packet. So, cycle time in case of an stop and wait protocol also includes acknowledgement. So, this is going to be a ratio of T of T divided by T of T plus 2 into T of T, which is we have just seen, which is you can say 1 upon 1 plus 2 into A, where A is T of P divided by T of T. So, this is actually you can say it is kind of a very simple calculation in order to calculate the efficiency, which is the total transmission time divided by your total cycle time of the packet. So, this is 1 upon 1 plus 2A, where A is T of P divided by T of T. Then with these terminologies, transmission, propagation delay, transmission delay, then we have looked into efficiency. Let us move on to the next one, which is effective bandwidth. This effective bandwidth is also known as throughput. Uh, Essentially, how are we going to define this throughput? Simply we can say number of bits sent per second. Now this effective bandwidth is denoted by EB. So this EB is equals to the data size divided by the total cycle time. So total cycle time we have already seen. Multiplying and dividing by bandwidth and using the convention where A is equals to Tp by T of t, as we have seen in, as we have seen just now. This is going to come up to 1 upon 1 plus 2a multiplied by b, or we can say this is actually efficiency into bandwidth. So net effective bandwidth or throughput, which is essentially defined as number of bits sent per second, is efficiency into bandwidth, and bandwidth is denoted by b, efficiency is denoted by, or efficiency as we have calculated in our previous slide or just now, is 1 upon 1 plus 2a. Moving further, if we look into the capacity of link, so now here comes the concept. Till this point we have looked into only the simplex communication. Now, as I have already told you at the starting of the lecture, that later on we will keep on increasing the restrictions. Now we have started looking into the full duplex channels. The full duplex channels, that means we are talking about that bits can be transferred in both the directions. But here we are again looking into, or we are again assuming that there are no collisions, because if there are collisions we need a separate mechanism to handle those collisions. So capacity of link in case of a full duplex channel, that is bits can be transferred in both the directions without any collision. Number of bits a channel or maybe a link can hold at maximum is its capacity. So whatever number of bits a channel or link can hold is going to be its capacity, and obviously we are going to like any channel or any link to attain its maximum capacity. So capacity here is going to be, or capacity of the link is going to be bandwidth multiplied by T of p. So and for full duplex channels, this is going to be, this capacity is going to be twice of this, because the transmission is going from sender to receiver and again receiver to sender, because the channel which we are considering is the full duplex channel. So till this point we have looked into kind of so many terminologies which are transmission delay, propagation delay, then we have looked into efficiency, then effective bandwidth, and finally the capacity of the link. Moving further to look into the sliding window protocols, we also need to understand the concept of pipelining. Now what was happening in our previous stop and wait protocol, only one packet was transmitted at a time. After sending that packet, the sender was waiting for the acknowledgement from the receiver before transmitting the next one. So the problem with this setup was kind of, we can say, low efficiency, because the communication channel is remaining underutilized. One packet is in the transmit. Even though more packets could fit into the channel during the waiting time, we are not allowed to send because of the kind of protocol restrictions. So if we talk about the total cycle time is T of t plus 2 T of p. Now if we look into how many packets could ideally be transmitted in one cycle time in case of stop and wait protocol, after the whole calculation, if we look into in T of t units, one packet can be transmitted. So in 1 unit it is 1 of T by T packets. Then the total cycle time is equals to T of t plus 2 of T p units. using our notation of A, packets per cycle is coming to, or is being, what we are able to determine is 1 plus 2a that we have seen. Now this 1 plus 2a, if we talk about the maximum packets then can be transmitted in the total cycle time. So after we have received the acknowledgement for packet 0 at the sender's end, we can say our kind of window slides maybe in a stop and wait protocol. Next packet can be assigned a sequence number 0, and we use the sequence numbers which we have acknowledged so that your header size can be kept as minimum. But the packets per cycle, if we say, is 1 plus 2a. Now this is actually a kind of we can say low number of packets if we talk about, and if the packet acknowledgement for the first packet is arriving in 3 milliseconds, then in a stop and wait protocol we will be able to calculate that only one packet is being transferred in 4 milliseconds. So now we want to improve it. So in this case we will be looking into sliding window protocol, in which a window of packets is maintained that have been sent out but yet not acknowledgement, and hence this mechanism allows us to send multiple packets to be transmitted efficiently, we can say. If we look into type of sliding window protocols, which we will be looking into, which we will be exploring in our further lectures, there are two types of sliding window protocols. One is go back N ARQ and the selective repeat ARQ. In go back N ARQ, multiple frames can be sent before an acknowledgement is received. If the frame is lost or an acknowledgement is missing, all the frames from that point onward are retransmitted. Again a problem or challenge to be taken care of. Selective repeat ARQ says multiple frames are sent before acknowledgement, but only the lost or erroneous frames are retransmitted, not all till that point. The receiver can store out of order frames until the missing ones arrive. So here what is being repeated is selective. In the another flavor, what is being repeated is not selective, it is from a point onwards all are retransmitted. So these two versions are available. We will definitely looking into these two versions of sliding window protocol into more detail in our upcoming lectures. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. Till then, take care. Goodbye.